The James Webb Space Telescope has flung open a portal to the past like never before, peering deeper into the universe's earliest history than any observatory before it. It has journeyed through the cosmic haze, reaching back 13 billion years to an era when the universe was still in its infancy. The images it has revealed have once again left the global astronomical community stunned and deep in thought. In the ancient universe, where chaos reigned and stars were just beginning to shine, scientists, through painstaking observations with the telescope, pierced through the dust clouds enveloping distant galaxies and stumbled upon three colossal ancient structures. Majestic yet eerie, they loomed like ghosts at the dawn of the cosmos. Now known as the Red Monsters, this awe-inspiring moniker perfectly captures their imposing nature. These structures are far more than ordinary galaxies. They are vast cosmic powerhouses, concealing intense energetic activities beneath a thick veil of dust. Their formation speed and mass scale defy everything we thought we knew about galaxy birth and evolution, shattering existing theoretical predictions. But what is the most mind-boggling discovery of all? It's when they existed. These three behemoths emerged a mere 500 million years after the Big Bang, a time when the universe was still expanding and cooling. Theoretically, only primordial gas clouds and nascent galaxy embryos should have existed then. Yet, there they were, fully formed and thriving. In this documentary episode, we will delve deep into the truth behind these red monsters, how they were discovered, why their very existence is so revolutionary to our understanding of the universe's essence, and what crucial missing pieces of the cosmic evolution puzzle they might reveal. This discovery came from the James Webb Telescope's Fermi Sky Survey, a pioneering observational mission that combines deep space imaging with high-resolution spectroscopy. This innovative combination has allowed astronomers to peer behind the curtain of dust and uncover the most cryptic secrets of the early universe. These three galaxies, dubbed the Red Monsters, stand out not only visually but also in terms of their size, mass, and the epoch in which they existed. Their appearance is almost like a sudden leap in the cosmic timeline. When researchers first analyzed the early data from the Webb Telescope, they noticed an abundance of unusually large, reddish dust-laden galaxies. These anomalies immediately piqued the interest of the astronomical community because, according to current models, they simply shouldn't have existed in the early stages of the universe. Through redshift measurements, scientists confirmed that these galaxies date back to a time when the universe was only 500 million to 1 billion years old, a period when the universe was still in its developmental infancy. At this stage, the universe was supposedly still struggling to assemble the first stars and galaxies. But what truly astounded the scientific community wasn't just when they appeared, but their sheer heft. Each red monster contains over 100 billion solar masses of stars, a figure that rivals or even exceeds the current mass of the entire Milky Way. They are like colossal metropolises born in the ancient cosmos. This discovery immediately raised a flurry of scientific questions and challenged existing theories. According to our well-established cosmological models, galaxies of this size should have taken eons to accrue mass and form. Yet, the red monsters seem to have skipped this process, growing rapidly and aggressively. Their deep red hue is the result of a double whammy of effects. First, the vast distance between them and us causes a redshift phenomenon, stretching the light they emit into the infrared spectrum. Second, the galaxies themselves are filled with dense cosmic dust, which obscures blue and visible light, making them appear an even deeper shade of red in our observations. Previous space telescopes like the Hubble, which primarily observed visible and ultraviolet light, were virtually blind to these dust-shrouded objects. They remained hidden in the observational blind spots. But the Webb telescope is different. Its near-infrared observation capabilities and highly sensitive prism spectroscopy technology have enabled scientists to lift the veil of dust and reveal a side of the universe that was previously invisible to other instruments. Using these advanced techniques, astronomers were able to accurately measure the redshifts of 36 candidate galaxies. Most of them fell within the expected range for early galaxy formation, but the three red monsters deviated significantly. Their extreme characteristics in terms of mass, density, and rate of evolution mark them as truly unique entities. This discovery, led by Dr. Menuhin Z, an astrophysicist from the University of Geneva, and her research team, was published in the prestigious journal Nature and quickly attracted intense attention and debate within the international academic community. But the story doesn't end with their size and mass. Even more astonishing is that these galaxies have already converted about half of their internal gas and dust into shining stars. This is an incredibly high star formation efficiency, far exceeding the typical levels seen in galaxies billions of years later, by 2 or even 3 times. Overall, these 3 red monsters may have accounted for nearly 17% of all star formation activity during that period of cosmic history. This is no small number. It's a wake-up call that forces us to reevaluate the speed and mechanisms of cosmic formation. Just 3 galaxies, seemingly insignificant in the vastness of the universe, could have had such a profound impact on early cosmic star formation. It's astonishing, almost beyond belief. Even more perplexing is the fact that their luminous glow isn't concentrated at the core. Instead, it spreads evenly across the entire galaxy. This structural characteristic stands in stark contrast to most galaxies we're familiar with, and it holds significant implications. In modern galaxies, intense radiation emanating from the core typically signals the presence of an active supermassive black hole at the center. Such black holes not only consume matter voraciously, but also release colossal amounts of energy, driving the furious activity in the galactic heart. However, observations of the red monsters tell a different tale. The light from these galaxies doesn't originate from an active galactic nucleus dominated by a black hole. Instead, it stems from widespread and synchronized star birth events occurring throughout the galaxy's a grand cosmic feast of star formation, as if the entire galaxy is ablaze, pulsating with growth. This discovery suggests that our understanding of the early universe might have been far too conservative. The first few 100 million years of the cosmos were likely a far more dynamic, efficient, and creative era than we once imagined. It wasn't a slow, steady march of development, but a soothing crucible of rapid evolution. This leads to a profound and pivotal question. How did these massive, mature galaxies manage to form and develop in such a short span of cosmic time? The emergence of the red monsters poses a direct challenge to the current standard model of cosmology, the lambda, cold dark matter CDM model. This model serves as the cornerstone of modern cosmology, outlining how the universe evolved from a uniform hot gas into the complex structures we see today. It integrates theories of dark matter, dark energy, and standard particle physics. According to the CDM model, galaxy formation is a gradual and protracted process. First, dark matter forms gravitational halos that act like cosmic traps. These halos then attract surrounding gas into their gravitational wells. Over time, through processes of cooling, compression, and fragmentation, stars and galaxies gradually take shape. Under normal circumstances, this process is rather inefficient, with only about 1/5 of the available gas ultimately transforming into stars. The rest of the gas is either heated or ejected from the galaxy due to feedback mechanisms, such as supernova explosions or jets from black holes. Such slow accumulation is thought to take billions of years to complete. Yet, the red monsters seem to flout this gradualist logic. They rapidly amassed staggering amounts of stellar mass in less than 1 billion years and converted vast quantities of gas into starlight in an astonishingly short time. This extraordinary growth rate and precocious development defy easy explanation within the existing model. Even the most sophisticated computer simulations based on the CDM model have failed to produce anything resembling these celestial behemoths. This exposes the limitations of the model under extreme conditions and hints that we may have overlooked crucial physical processes that occurred in the early universe. If we wish to preserve the overall framework of the CDM model, we must find ways to adjust it to accommodate these unprecedented anomalies. One possible avenue for revision is to postulate that the early universe had a more conducive environment for galaxy formation than previously thought. For instance, higher average gas densities could have enabled more efficient cooling and collapse of gas clouds, allowing gravitational collapse to reach critical points more quickly and trigger large-scale star formation. Alternatively, galaxy mergers might have been far more frequent in the early universe. These mergers not only added mass, but also altered physical conditions, such as increasing gas compression and turbulence, thereby accelerating galaxy assembly and star-forming bursts. However, Any adjustments to the CDM model must be made with extreme caution. We cannot undermine its remarkable success in explaining other aspects of the universe, such as the structure and temperature fluctuations of the cosmic microwave background, the large-scale distribution of galaxies, and the statistical patterns of element formation and diffusion. Over-tinkering with the model to account for the red monster's risks, shattering our comprehensive understanding of these other phenomena and fragmenting the entire theoretical framework. This is precisely why the red monsters cannot be dismissed as mere anomalies or outliers. They are crucial touchstones that test the viability of our theories, representing both a challenge and an opportunity. They compel us to redefine the boundaries and tolerances of our theoretical models, driving us to refine them further so that they can encompass even the most extreme cosmic scenarios while maintaining their explanatory power across a wide range of observations. Another dimension of this theoretical conundrum involves the so-called feedback regulation mechanisms, the cosmic self-regulatory processes that prevent runaway star formation. In standard theory, when a large number of stars form, these young stars emit intense radiation and stellar winds. When they eventually explode as supernovae, they release an enormous amount of energy. These mechanisms heat the surrounding gas and can even expel it from the galaxy, thereby suppressing further star formation. This negative feedback typically serves to slow down the rate of star formation, creating a rhythmic pattern of cosmic evolution. But in the case of the red monsters, this cosmic braking system appears to have malfunctioned, or at least been significantly delayed. They seem to have broken through the normal regulatory mechanisms, achieving an astonishingly high rate of star production in an incredibly short time, almost like a cosmic inflationary event in the realm of galaxies. This raises new questions. Were these feedback mechanisms inherently weaker or less developed in the early universe? Or did these galaxies grow so rapidly that the feedback mechanisms simply didn't have time to kick in? Regardless of the answers, the red monsters force us to re-examine the rhythms, laws, and limits of cosmic evolution. Like three anachronistic fossils, they serve as a powerful reminder that the early universe was far wilder than we could have ever imagined. The common drivers of extreme luminosity in the Milky Way active supermassive black holes seem notably absent in these red monsters, or at least not serving as the primary energy engines. This starkly contrasts with later cosmic epochs. In the billions of years that followed, numerous galaxies we observe, especially satellite galaxies and active galactic nuclei, are often dominated by central black holes. These black holes not only devour matter voraciously, but also emit intensely bright radiation, illuminating the very heart of their host galaxies. Yet, in the case of the red monsters, it is the multitude of widely dispersed young stars that form the main source of light. The entire galaxy functions like a vast stellar factory, igniting starlight across multiple regions simultaneously, powering its dazzling infrared emissions. This difference in galactic energy structures carries profound implications. It could signify a fundamentally distinct path of galactic evolution, a unique developmental mode exclusive to the universe's first billion years, which either vanished or transformed afterward. Alternatively, another possibility looms large. These galaxies may not be as rare as they seem. Instead, they might have long remained hidden behind cosmic dust veils, beyond the observational reach of the Hubble Space Telescope and other early-era observatories. Only with the advent and deployment of the James Webb Space Telescope have we been able to glimpse them for the first time. Regardless of the explanation, the message is clearer and even alarming. Galaxy formation in the early universe was far more complex, diverse, and creative than our previous theories allowed. The discovery of the red monsters has undoubtedly ushered in a new era of observational cosmology, resetting our understanding of the scale and possibilities of early universe star formation. However, their emergence also poses a crucial question demanding immediate answers. Are these three galaxies rare oddities in nature, or do they merely represent a much larger, overlooked population? To unravel this mystery, astronomers are gearing up for more in-depth and wide-ranging surveys. No longer content with sporadic observations, they plan to conduct systematic censuses. The James Webb Space Telescope will continue to leverage its exceptional infrared sensitivity to explore the most ancient reaches of the universe, searching for more celestial bodies like the red monsters. Meanwhile, the Otto Large Millimeter, Millimeter Array ALMA will utilize its precise high-frequency band observation capabilities to measure the cold gas and dust content essential for star formation within galaxies. The combination of these two observational approaches will provide us with a more complete and high-resolution map of early-era galaxies. One of the primary observational goals is to assess how much available cold gas remains in these red monsters. This data will reveal whether they are still in an active phase of star formation or approaching a bottleneck and saturation point in their galactic development. ALMA's capabilities will shine brightly here, as it can detect molecular gases within galaxies, especially carbon monoxide, a telltale gas indicating star formation, and thus estimate the total amount and distribution of gas. Another line of investigation lies in the chemical composition of these galaxies. We know that the first stars in the universe, so-called population 3 stars, were composed purely of hydrogen and helium, as heavier elements had not yet formed. They were primordial flames devoid of metals. However, the observed dust content in the red monsters suggests that heavy elements were already abundant and dispersed, implying that supernova explosions and the enrichment of stellar metals occurred earlier and more violently than predicted. This could further upend the existing timeline of stellar population transitions, how the first-generation stars evolved into subsequent populations, how they produced metals through explosions and dispersed them throughout the galaxy. Understanding the feedback mechanisms in these galaxies is also key to future research. If these early giant galaxies truly formed without being constrained by traditional feedback mechanisms, astronomers must delve into why supernova explosions and radiation pressure failed to exert their expected inhibitory effects in these systems. One possible explanation is that as the entropy of dark matter increased rapidly, the gravitational binding energy of the galaxies also grew swiftly, making it difficult to expel gas and thus weakening the effectiveness of feedback. Or perhaps there are still unrecognized processes at play. Maybe early-stage black holes did not participate in energy regulation, or abnormal physical conditions within the galaxies prevented energy from being effectively transferred to the galactic outskirts. These are all crucial variables yet to be incorporated into simulations. Future theoretical models must account for these complex possibilities. If these observations expand further, and instead of just 3 red monsters, we discover an entire population of overlooked early giant galaxies, we may also need to reevaluate the timeline of cosmic reionization. The epoch of reionization marks when the first stars and galaxies released sufficient ultraviolet radiation to reionize hydrogen atoms in the universe, transitioning it from the dark ages to a transparent, observable state. The presence of a large number of galaxies on the scale of the red monsters could significantly accelerate this transition, altering our fundamental understanding of when and how the universe became transparent. But perhaps the most humbling aspect of this entire narrative is this: despite our sophisticated theories, numerical simulations, and cutting-edge technologies, the universe continues to surprise us in the most unpredictable ways. The red monsters serve as a wake-up call, reminding us that our knowledge of the cosmos is always an unfinished sketch. We once believed that galaxies required vast amounts of time, stable environments, and gradual evolution to form. Now, we've witnessed a different kind of universe, one characterized by rapid, intense, and spectacular bursts of growth in its earliest chapters. This story is far from over. As more observational data floods in and theoretical models are refined, we may find that the early universe wasn't just prolific. It was a wild experimental ground full of risks and wonders. The red monsters are the remnants of this cosmic experiment, powerful, mysterious, ephemeral, yet profound. They are not distant illusions but whispers from the universe's adolescence, holding truths we have yet to decipher. As we gaze upon these 3 red monsters, it's as if we're peering into a lost chapter of the universe written on the edge of time, an unexpected and unanticipated part of history. They are both a challenge and an inspiration, forcing us to re-examine how the universe came into being and evolved, reminding us that this vast cosmos has never followed a linear path or adhered to a predictable script. Perhaps within the first glimmers of the universe, there lies an order we have yet to name, a rhythm that flickers between chaos and creation. And we are only just beginning to learn how to listen. The red monsters are not the answers, they are the questions themselves, a nameless letter from the universe, sent 13 billion years ago, still waiting to be opened, understood, and revered.